growing from ancient astronomical observations 2,500 years ago to black holes in space. No human endeavor has transformed society and defined our place in the cosmos more than the physical sciences. What started as a kernel of knowledge about the movement of the heavenly bodies has expanded to include the atomic building blocks of all chemistry, geology's understanding of Earth's long history and the forces that have shaped our planet's features, astronomy's picture of an ever-expanding universe populated by billions of galaxies, each containing billions of stars, and physics' understanding of the basic principles of movement, energy, and forces which have given us the technological world of cars, planes, television, computers, cell phones, and the electrification of the planet. Turning Points in the Physical Sciences takes you on an exciting journey of discovery from ancient through classical science to the world of modern physics, relativity, chaos theory, and quantum mechanics. Early astronomers looked into the night and saw the moon, the planets, stars, and the occasional comet. But they also saw small hazy spots called nebula. In fact, Ptolemy recorded 7 of these nebulas that were visible to the naked eye. By the late 18th century, over 100 of these curious objects had been catalogued and given M designations by the French astronomer Charles Messier, such as M31, the Great Andromeda Nebula. At the same time, astronomers were not sure what these nebula were. By the middle of the 19th century, using powerful new telescopes, some of the Messier objects were resolved into gaseous dust clouds, true nebula. Others turned out to be dense collections of stars called globular clusters. A third group appeared spiral in nature. In 1850, English astronomer William Parsons sketched the first galaxy without really knowing at the time what it was. Ever since Copernicus removed the Earth from the center of the universe, astronomers have believed that the sun must be the center of our galaxy, a luminous flat belt of stars known as the Milky Way. The size of the galaxy remained a mystery until 1918 and the completion of the new 100-inch telescope at the Mount Wilson Observatory in Southern California. Harlow Shapley, an American astronomer working at the Mount Wilson Observatory, performed some calculations on a peculiar type of star called Cepheid variables, whose output of light varies periodically with time. He concluded that our sun was not the center of our galaxy. Instead, the sun was on the edge of the Milky Way. The question remained, was it the only galaxy? A few years later, using the same telescope, American astronomer Edwin Hubble discovered that ours was only one of many galaxies. Hubble classified these galaxies into normal spirals, barred spirals, ellipticals, and regulars. At first, he believed the shapes represented an evolutionary progression, but later changed his mind. By the 21st century, it was determined that there are billions of other galaxies. Hubble's observations did not stop with the discovery of other galaxies. During the 1920s, Hubble and his colleagues measured the redshift of 49 galaxies. And to their surprise, every galaxy was moving away from us. In fact, the more distant ones were moving faster. These astonishing facts forced Hubble to conclude in 1929 that the universe was expanding and that there was a definite moment of creation. Later scientists called this moment when the universe came into existence the Big Bang and put it at about 13 billion years ago. In an odd twist, since an expanding universe means everywhere is the center, humans once again found themselves at the center of the universe, or even more oddly, there is no center at all. Albert Einstein's famous equation from special relativity, E equals mc squared, promised that every tiny bit of matter contained an incredible amount of energy. The question was, could it be released? In the 1930s, the constituents of an atom's nucleus, protons and neutrons, were being used to bombard the nucleus of other atoms. By the middle of the decade, lithium atoms had been split into 2 helium nuclei. Nuclear fission, as it was called, was fulfilling the dream of ancient alchemists, transmuting elements. However, once out of the bottle, the nuclear genie was about to prove deadly. In 1938, German scientists Otto Hahn and Fritz Strassmann used neutrons to blast the uranium nucleus. The surprising result was that the uranium atoms split into barium, throwing off at the same time 2 neutron particles. Interestingly, there was less mass in the resulting new products of this nuclear fission. The missing mass had been converted to energy. In short, the German scientists had discovered the possibility of a new, powerful bomb. As World War II began, Americans, fearful that the Germans would build such a weapon, started their own super-secret project to build a nuclear weapon. It was called the Manhattan Project. It had been surmised by such physicists as the Italian-born Enrico Fermi that the neutrons given off by the split of the uranium atom would go on to split other atoms in a chain reaction. Controlled and slowed by a neutron-absorbing carbon and cadmium chamber, the first nuclear chain reaction took place in 1942 on the University of Chicago campus. The conclusion was obvious. A controlled chain reaction could provide tremendous usable power. An uncontrolled chain reaction would explode with devastating power. At Los Alamos, New Mexico, the first atomic bomb was set off in the summer of 1945. A few weeks later, American armed forces dropped 2 bombs on Japan, ending World War II. In 1957, fission energy was first used to generate electricity. By the beginning of the 21st century, 1/5 of the world's electricity was coming from nuclear reactors. After World War II and the success of nuclear physics, the frontiers of science turned to the very small and the vastness of outer space. With the building of larger and new kinds of telescopes, such as radio telescopes, astronomers were poised to take a new look into the universe and see what was out there. In the mid-50s, radio astronomers were puzzling over an ever-growing list of mysterious radio sources in deep space. When looked at by light telescopes, these phenomena, called quasi-stellar radio sources or quasars, showed up as star-like objects, point sources unlike the associated radio emissions that were quite broadly spread out. When viewed spectroscopically, quasars were just as mysterious. In 1963, American astronomer Martin Schmidt determined the spectral oddness was, in fact, the product of an extreme redshift, galaxies moving away from us at an incredible rate. Quasars were nothing more than the highly active core of a developing galaxy. It was speculated in the latter part of the 20th century that these galaxy cores were in the early stage of development, intense areas of massive explosion associated with a black hole, an area of supergravitational pull. Interestingly, there are no nearby quasars, further suggesting that they are from a more ancient time in the creation of the universe. When the neutron was added to the model of the atom in 1932, there was a certain feeling among physicists that the search for the building blocks of matter was complete. However, even before World War II and the atomic bomb, numbers relating to the energy levels of some subatomic interactions did not always add up. To solve this problem, Austrian physicist Wolfgang Pauli postulated in 1930 a new fundamental particle that Enrico Fermi named the neutrino, the little neutral one. Much of science wondered, was a neutrino just a mathematical contrivance, or could it actually be detected?
Are three clues you have to tell you whether or not it's really due to a neutrino.
After the war, armed with new tools such as bubble chambers, atom smashers, and particle accelerators, physicists began anew the search for fundamental particles.
And so it would look like a neutrino, but it would be out of time with the beam.
One of the first successes of this new era of atomic exploration was the detection of the neutrino. Using these new tools, they discovered over 100 new supposedly fundamental particles, including the positron, antiproton, pions, muons, and kaons. Then in 1964, American theorist Murray Gell-Mann announced to the world that the proton and neutron were not elemental. They were actually made up of more fundamental particles called quarks, which he had given rather colorful names: up, down, charm, strange, top, and bottom. For example, protons are made up of 2 ups and 1 down. Quarks were negatively and positively charged in thirds. By the end of the 20th century, all 6 quarks Gell-Mann postulated had been detected. Many physicists believe there is a deeper and simpler reality behind this new proliferation of particles and the forces that control their behavior. Attempts at such a unification have included Maxwell's equations when he showed that magnetic and electrical fields were actually one unified field. And more recently, superstring theory, advocated by Stephen Hawking, where all of existence is notes plucked on a string. Looking up at the night sky, nothing seems more unchanging than the stars in the firmament. Yet behind this seeming permanence is a great story of change. In the beginning, the Big Bang created the universe. From this tremendous explosion, hydrogen and helium spread outward for hundreds of millions of years in an ever-expanding darkness. Then there was light. A star formed, radiating heat and light through the process of nuclear fusion. Turning hydrogen into helium, a star begins a journey that eventually ends in death. Studying the death remnant of stars opened up a whole new era of cosmological discovery for astronomers in the 20th century. In the early part of that century, astronomers understood that eventually the hydrogen in the star, like our own sun, would run out. When that happens, a red giant emerges as the star's core collapses and helium is converted into carbon and other high-mass atoms. From this point, a star can produce one of three kinds of cosmic cinders. A less massive star, like our own, goes through a process of shedding its outer layers, leaving behind some of the most beautiful objects in the heavens, planetary nebula. What remains is what British astronomer Arthur Eddington correctly identified as a white dwarf in 1931. A super-dense, stable star about the size of the Earth. But not all stellar deaths are so peaceful. Instead, they die in one of the most violent events in the universe. A supernova, like the one witnessed in the Crab Nebula in 1065. When this happens, one possible stellar remnant is a neutron star, such as the one found to be contained in the Crab Nebula. Neutron stars are super dense, smaller than white dwarfs, and made up primarily of neutrons. In 1967, Jocelyn Bell, a young British research student in radio astronomy, detected strange radio signals with a repetitive pattern. At first, she and her colleagues thought it might be aliens trying to communicate. They even gave them LGM numbers, little green men numbers. But the signals turned out to be not aliens, but pulsars. Pulsars are neutron stars that rotate through their own intense magnetic field, in the process pulsing out high-energy radiation. While there are billions of neutron stars, by the start of the 21st century, only 1,000 pulsars had been discovered. But the most science fiction-filled stellar remnant is the black hole. As early as 1784, John Mitchell introduced the idea of black holes, massive objects that would not allow light to radiate or particles to escape because of their intense gravitational pull. But science fiction became reality when in 1965, the stellar companion of Cygnus X1 was determined to be a black hole. One of the characteristic properties of black holes is that they often rip matter from nearby stars, producing intense X-ray radiation. Such X-ray characteristics have been found to exist at the center of many galaxies, leading astronomers to surmise that black holes are essential to the creation of those galaxies. Stellar death is stellar rebirth. One way to understand the differences between dead stars is that a 100-pound person on Earth would weigh a ton on our sun, 10,000 tons on a white dwarf, 10 billion tons on a neutron star, and 30 billion tons on a black hole. So behind the seeming permanence of the night sky is a great play of life as stars evolve and die, all part of the Big Bang's ever-expansion of the universe. As the 20th century came to an end, astronomers with their powerful new telescopes could see that the billions of detectable galaxies were not laid out randomly. They were in clusters and superclusters that spread out in filaments throughout the cosmos. Some large-scale organizing principle must be at work. But what was it? One such principle already known as the Hubble flow. stated that all galaxy clusters move away from each other at the speed proportional to the distance from the observer. In 1990, American astronomers Alan Dressler and Sandra Farber found that our own supercluster was not following the flow predicted by Hubble's constant. Instead, it was being drawn towards the constellation Centaurus. What was doing the drawing was given the colorful name, the Great Attractor. But what is the Great Attractor? Early in the 21st century, astronomers speculated that the most likely culprits are mysterious centers of intense gravitational pull. Given the even more colorful name, dark matter. It is estimated that whatever dark matter is, it makes up most of the material in the universe. Astronomers now estimate that 85 to 95% of all material in the universe is dark matter. Its characteristic is an intense gravitational field from which no particles or radiation can escape. In comparison, visible matter, electrons, neutrons, and protons, make up only a tiny percent of the known universe. Discovering the nature of dark matter and determining whether it is the organizing force behind galaxies and their distribution is one of the great challenges for physicists and astronomers in the 21st century. When in the spring of 2004, NASA announced that the Hubble Space Telescope had detected a planet outside our solar system with the building blocks of life, oxygen and carbon, science had once more redefined our place in the cosmos. Western science began in Greece when ancient astronomers looked into the sky, searching for order behind the movements of the heavenly bodies. Their search for the laws that governed these movements began a 2,500-year saga that has continually reshaped how we looked at ourselves and the world around us. They also asked, was there a hidden reality behind the matter of everyday life? What was stuff made up of? The first answer was earth, fire, air, and water. Then 18th century chemists showed that matter was made up of elements such as oxygen and hydrogen that combined to produce water. Hence the atomic theory of matter was born. Earth and air would go on to make up the study of the planet, the sciences of meteorology and geology. Geology showed that the planet had a long history. Its features were shaped by the natural processes of erosion, volcanism, glaciation, and the movement of the continental plates. Fire, or heat, was found to be a form of energy. Energy was defined to be the ability to do work and could be converted into other forms of energy: mechanical, chemical, and electrical. The study of the mysterious forces of electricity and magnetism were united into one magnificent theory when light was found to be made up of a field of electricity and a field of magnetism. Electromagnetic radiation, which not only included light, but radio waves, microwaves, X-rays, and gamma rays, propelled the technological revolution that created our modern world. Fields such as gravitational fields were now a cornerstone of the physical sciences. While some scientists examined the larger world around us, others looked in the minute world of the atom. It was found to be made up of parts, electrons, neutrons, and protons. They, in turn, were made up of quarks. Very quickly, other subatomic particles were discovered. Explaining the behavior of all these particles led to quantum mechanics and the power and weirdness of modern physics. By the middle of the 20th century, astronomers looking outward using powerful new telescopes discovered our sun was just one of many suns in a galaxy of billions of stars. And there were billions of galaxies. Galaxies, along with all matter, even space and time themselves, had a unique beginning called the Big Bang some 13.7 billion years ago. When science entered the 21st century, so much had been discovered. With over 100 extrasolar planets now cataloged, some with life's biomarkers, oxygen and carbon, it is clear that we are not alone in the cosmos. What is even more clear is that the search for the simple laws that govern all motion and the answer to the question, what are the final fundamental elements of reality, has not been fully answered. Both pursuits are just as alive today as they were when the ancient Greeks began the search 2,500 years ago.